on here and introduce some of the factors that affect force generation by an individual muscle fiber. So we've been speaking about muscles generating a set amount of force, but how can we change that? How can we make muscles generate more force? How can we build up muscle strength? How can we go to the gym, work out, bulk up so that we can lift heavier objects, right? How do we actually do that from a histological and biochemical perspective? So muscle contractions are dependent on two things. The tension that's produced by a single fiber, right? Remember, a muscle, like the biceps muscle, is really made of several different fibers. Fibers are like the cells, the individual units of that muscle. So the amount of force being produced by each of those fibers will then affect the amount of force that the entire muscle can generate. Now, going a bit further, the amount of tension produced by a fiber is dependent on the number of cross-bridge cycles. So how many actin and myosin interactions are being made. If we have more cross-bridge cycles being made, we can generate more force, we can overcome heavier loads. The other thing that is dependent is the number of fibers that are contracting. Now, when you're lifting things every day, I'm lifting a piece of paper, again, my phone, a pen, light objects, the entire muscle is not actually contracting, right? It's not usual that all of our muscle fibers are contracting. Depending on how heavy that load is, that will determine how many of the fibers in that muscle group are actually contracting. All right. So for example, although I'm using my biceps to lift this piece of paper, maybe 5 or 6 fibers within the biceps group are actually contracting. The others are just chilling out because this is a relatively light load and we don't need a whole lot of force or tension to overcome a piece of paper, right? All right, so the two main factors that determine how much force a muscle generates are the tension produced by each fiber, and then how many of those fibers are actually actively contracting. All right, let's talk about the frequency of stimulation. So because we said back here that the number of cross-bridge cycles can determine how much force we generate, we want to think about the frequency of muscle stimulation. If we stimulate a muscle more faster, that is, we fire more action potentials more frequently, we can stimulate more contraction, more cross-bridge cycling, right? More calcium being released, more exposing of those myosin binding sites, more cross-bridge cycling, more force. So one of the first factors that influences how much force a muscle can generate is how fast we can stimulate that muscle. In other words, the frequency of action potentials. Now, based upon that understanding, there are two ways that we can increase the frequency. There are two phenomena that we want to talk about here. The first one is called trap. And trap is this idea that if I were to fire one action potential, I would generate X amount of force, then the muscle would relax. If I were to fire another action potential, I generate slightly more force, then the muscle would relax. I'm going to fire another action potential, the muscle would generate more force, and then it would relax until I get to a plateau, which is the maximum amount of force that this muscle can generate. Okay, that idea is called trap. If I increase the frequency of stimulation, so these action potentials are coming in pretty rapidly behind each other, right? Pretty rapidly in succession, I will increase the amount of force that is being generated. Now, the reason we have trap is not entirely understood. So because the muscle actually relaxes in between each of these contractions, we can't say that calcium is still in the sarcoplasm. We can't say that the muscle did not relax, and so that's why it's producing more force. And so we really don't know why trap exists. Why is it that if I stimulate this muscle, allow it to fully relax, the next time I stimulate it, it somehow generates more force, right, easier, right? So we know that this happens. This is called trap, but we're not exactly sure why it happens. Okay, let's differentiate that from summation. And summation is when we have the summing of several different impulses coming in on the muscle. So essentially, we have an action potential here. So this is the length of time for a single action potential versus the length of time for an entire twitch. And so what we can see is that we can have several different action potentials summing together in the time that it takes for a single twitch to occur. So because an action potential is anywhere from 1 to 2 milliseconds, and a contraction is anywhere from 10 to 200 milliseconds, the contractions can overlap and they can sum if several different action potentials are coming in before one action potential is complete. Or sorry, before one twitch is complete, one contraction is complete. All right, so this is what summation looks like in succession. So we stimulate this muscle once here. We generate a set amount of tension or force. We then relax the muscle, okay? We stimulate it again, right? We contract. And then because we don't fully relax, with summation, the relaxation is not complete. With trap, we did see full relaxation. And that's the difference between trap and summation. So because we don't see full relaxation in between this contraction and the subsequent action potential, which is allowing for another contraction, we then see that these contractions start to overlap. They start to kind of sum together. So we stimulate we fire another action potential that stimulates the muscle again. The relaxation of this first contraction had not fully taken place. And so we're not starting from a 0 point of tension, we're starting from a midway point of tension. And so that is why the next time we would generate more force. Okay, and then we do that again. We stimulate a third action potential here. This is starting from this midway point, so it's not fully relaxed. And so the next time we contract the muscle, it's going to generate slightly more force. So we can explain, we can rationalize summation, because if the muscle does not fully relax, it would make sense that the next time you stimulate it, it would generate even more force. But we cannot really explain or rationalize trap because we do see full relaxation, but starting from 0, and then somehow we generate more force the next time. Now, if we were to continue increasing the frequency, so these action potentials now are being fired closer and closer in proximity. This is being fired more frequently. We're going to start to see what's called incomplete tetanus or unfused tetanus, okay? And that is where we have the amount of tension being produced kind of just staying constant. So the muscle not really relaxing or not really producing more force, but the amount of contraction kind of just averaging out close to its peak contraction. And then if we were to increase the frequency of action potentials even further, we would get to a state that's called complete tetanus or fused tetanus. This is where the muscle is completely contracting at its maximum, at its absolute peak, but absolutely 0 relaxation is happening, okay? So it's not relaxing even just a little bit, it's just staying fully contracted. These contractions are completely fused, and this is called complete tetanus, okay? And so this is the kind of sequence of events that we go by simply increasing the frequency of action potentials or increasing the frequency of muscle stimulation. All right. Again, here, just explaining the reason that we see summation. So the amount of force that is developed depends on how much calcium is bound to troponin. So again, connecting back to that excitation contraction coupling, if there's a lot of calcium flooding the sarcoplasm, binding to troponin, we're going to have a lot of exposing of those myosin binding sites. We're going to have a lot of cross-bridge cycling. We're going to have a lot of force generated. So if we can stimulate the muscle really quickly, there's less time for it to fully relax. And so all of that calcium is not going to leave the sarcoplasm. A lot of it is still going to be staying around. And so the next time we contract, we're going to start out from a place where the sarcoplasm already has a lot of calcium there. And so we're going to be able to generate more force by flooding more calcium out into that sarcoplasm, okay? So we eventually get to a place of maximum tetanic contraction. This is if we max out all of our troponin. So this is where the system is completely saturated. All the troponin has calcium bound to it. And so even if I were to stimulate the muscle even more, I could not generate any more force because I could not generate any more cross-bridge cycles because I could not generate any more calcium binding to troponin, right? So the entire system is completely saturated, and this is called a maximum tetanic contraction. All right. Now, this is kind of linked to tetany. If you've heard of tetany, this is spasmic muscle contractions. It's usually caused by calcium imbalances. It can be caused as a reaction to medications and drugs as well. So this is where the muscles are completely stiff and rigid with that tetanic contraction because of the fact that so much calcium is flooding the cytoplasm. The system is saturated and the muscles are rigid because they're stuck in this maximum contracted state. All right. Okay. And that is different from tetanus, by the way. You may have heard of tetanus, which is a bacteria, right? You usually get your tetanus shot. That's an entirely different thing from tetany, which is caused from calcium. All right. Let's pause here and see what questions we have. I think we'll leave it at that for today, but in the meantime, I'll see what questions we have. So just to reiterate what we discussed today, we talked about the twitch, we talked about what a twitch is. We then went on to talk about the phases of a twitch, so the latent period, the contraction phase, the relaxation phase. We then spoke about the types of twitches, so the isometric contractions, which is where we can't overcome the load, versus the isotonic contractions, which is where we can overcome the load. And then we recently, or just at the end here, introduced this idea of things that we can do to stimulate more force generation. And the things that we've said so far are, if we increase the number of fibers that are contracting, and if we increase the amount of cross-bridge cycles that are happening on each of those fibers.